Good evening, Shevington. A pleasure to be here to tell you a little bit about astrophotography with an emphasis on how you can do some astrophotography without shelling out thousands of pounds. You can do that if you wish. I'm going to give you an alternative. So I'll say a little bit about how you can start in astrophotography very simply, just with a camera on tripod. I'll tell you a little bit about the expensive way of doing it by buying telescopes and rather sophisticated mounts to put those telescopes on. Then I'll be telling you about the cheapest way of doing astrophotography, which is using a so-called tracker, which I'll come to in due course. And then I'll use this talk as an excuse to show some of the images that I've taken with my camera and my tracker. And I'll finish with a few thoughts about how you can get some nice images from really remote places like, for instance, darkest Africa, where you can really get away from light pollution. So let's start with just what you can do in terms of astrophotography, just with a camera and stick it on top of a tripod and see what you get. This is a picture taken some time ago. Where possible, I've given details at the bottom. This was taken quite a few years ago, before I went digital. So this was taken with an SLR camera and Fujichrome slide film. And this is something like a 5-minute exposure. Literally, camera on tripod, open the shutter for 5 minutes, having pointed it north, and see what you get. I know this is north because the North Star is there, which doesn't seem to move as the Earth rotates, but all the other stars seem to be trailing. I can tell it's 5 minutes just by working out how long that trail is. That is literally 5 minutes. If you think of 5 minutes as a fraction of 1 day, it tells you how long these star trails are going to be. And the only real bright star that doesn't seem to show a trail is the North Star Polaris, which sits coincidentally very close to the North Pole. In other words, the North Celestial Pole, which sits directly above the North Pole of the Earth. So that was a wide-angle lens, one of the simplest way of taking star trails. Now that we are digital, we're no longer limited to saying, well, how long do I have to keep the shutter open and how do I avoid anybody walking in front of my camera whilst I'm taking my pictures? Now that I'm assuming most of us are digital, there are alternatives. You don't have to take one long exposure. You can, if you wish, take lots of relatively short exposures. And then software, either free software or software you can pay for if you prefer, can add up all of those images together and give you the final result. So you can end up with images like this. In this case, this is 6 hours, not a single 6-hour exposure, but 360 exposures, all of which were 1 minute, and then software basically added them all together to give us the result that looks like a 6-hour exposure. It almost looks like a daylight picture because this was taken at an observatory. It was actually taken at Mount Tidy, where we take our students. University of Liverpool and Liverpool John Moores University take students out to Mount Tidy Observatory in Tenerife to give them an experience of dark skies. You might say that doesn't look very dark, the sky looks very blue. Well, yes, there was a full moon this night. Hence, the sky looks blue rather than black, and hence the foreground looks almost sunlit because of a bright full moon. But as well as adding together the images to give you the equivalent of a 6-hour star trail, you can also ask the software to say, well, don't just give me the final result, show me how it adds up, image by image by image, and then you get this effectively a movie of all the stars rotating around the pole star. The pole star, again, being the one that hardly moves at all while everything else rotates around. Doing it like this has a lot of advantages. Taking a lot of short exposures means that if one of those exposures is ruined by somebody walking in front of the camera or a satellite going by or an aircraft going by, it doesn't ruin the entire result. So you have a lot of power taking a lot of short exposures and adding them together. And generally speaking, that is just a much easier way, because we can do that with digital photography. That's a much easier way of working. Some astrophotography just has to be right place, right time. If you want to catch a total eclipse of the sun, you have no choice but to go where a total eclipse of the sun is visible. Friends and I went down to Cornwall in 1999, were disappointed by being under cloud, and so a few years later we decided to go somewhere where we thought there's unlikely to be cloud. We went to the Sahara Desert, and there we saw this beautiful eclipse of the sun. Again, you don't need any fancy equipment. This was a telephoto lens sitting on a tripod pointed at the sun. You need filters whilst the sun is visible, but as soon as the sun is covered by the moon, then you can just take long-ish exposures of a fraction of a second without worrying about any problems. And this particular eclipse lasted for about 4 minutes or so. But similarly, right place, right time, it's a question of if you want to see the northern lights in all their glory, ideally the Arctic Circle or thereabouts, somewhere like Iceland, where this was taken, or Scandinavia, you can get beautiful images of the entire sky lit up. Again, you don't need any fancy equipment. Probably a wide-angle lens is best, sitting on a tripod, pointed at the sky. This, again, was before I went digital. This is quite a few years ago, and so this was probably a few minutes exposure. I would like to go back to Iceland another day with a digital camera because the exposures can be shorter, and then some of the shimmering effects that get blurred out by the longer exposures will hopefully be captured by digital photography. So one day I hope to improve on these images. And it's wonderful just to go out at night and see the entire sky lit up with reds and greens as the aurora takes hold and displays for many, many hours. Some of you might have caught a tail end of the aurora as it came down to the UK. You don't get quite the same structures, you don't get the same spectacle. In many cases, you can't actually see anything, but you can capture a little bit of color if you point your camera at the sky. So this was taken from my bedroom window, and you get a little bit of the greens and reds coming through, but you don't see all of the spectacle that you see if you go to northern latitudes, such as the Arctic Circle. So let me tell you a little bit about moving on from simply having a camera on a tripod, pointing at the sky and hoping for the best. If you've got deep enough pockets, you can decide, if you're getting serious in astronomy and astrophotography, that you might want to buy yourself a telescope. Okay, fine. How do you go about that? Well, one option is to go for the best telescope money can buy. So there's the Hubble Space Telescope. It's now 35 years old, launched in 1990. They are going to be retiring it soon, so yep, keep an eye on eBay. It's going to be available at some point, but unfortunately buyer collects. That's the main problem. So yeah, you don't need a Hubble Space Telescope to take spectacular images. That's one way of doing it, of course. If you've got a few $1 billion, you can take absolutely wonderful images like these from the Hubble. These were released back in the 1990s and the noughties, the famous pillars of creation that, in a sense, made it famous. I'm labeling some of these, by the way, if you're not familiar with them. A lot of these objects are defined by a catalogue put together by a certain Charles Messier, and so they're referred to as Messier numbers or Messier M numbers. So M51 and M16 are simply shorthand for these particular objects. If your budget doesn't stretch to $1 billion, even second-hand for the Hubble Space Telescope, there are other options. For instance, you can buy yourself a 747. This is a 747 with a telescope in the back there, looking at the sky by opening up the rear door. It's got an oversized tail to keep it nice and stable. You notice that this is run by NASA. It's called SOFIA, the Stratospheric Observatory for Infrared Astronomy. This was doing infrared astronomy and is now being retired, partly because it's been superseded by the James Webb Space Telescope, which was launched in 2021. So again, this has now been retired, so I'm not sure about eBay, but maybe they'll be selling it off second-hand if you fancy a telescope that flies at 10,000 meters. The idea being that if you fly at 10,000 meters, you're flying above most of the atmosphere, and the atmosphere tends to be turbulent and tends to blur any details. That's why we have space telescopes. But in a sense, halfway to space, 10,000 meters or so, gets your telescope above most of the absorbing effect of the atmosphere. If your pocket doesn't stretch to 100 million, well, for a mere few million, you could buy something like the Liverpool telescope. The Liverpool telescope, built in Liverpool but operated in La Palma in the Canary Islands, It's a fully robotic telescope, so you don't have to go there to use it. You can use it robotically by simply putting in instructions via the internet. And that will give you some very nice images. Again, there's the pillars of creation, and again, the spiral galaxy, the whirlpool galaxy, otherwise known as M51. So if £1 million, if we haven't yet got to your budget, I'm bringing this down as far as I can, if you've got somewhere north of a few £100s, I would argue if you've got less than £100, you might be better off with a pair of binoculars rather than the telescope. But if your budget stretches from a few £100s to a few tens of thousands of pounds, then you have a huge number of amateur telescopes to think about. It is a bewildering number. I've got a catalogue, a brochure if you like, and it's got something like 100 pages. Each of those pages might have a dozen different telescopes on them. So there are literally thousands of different types of telescopes just available within the UK. And it's rather bewildering in terms of trying to decide which of those might be a good purchase, regardless of whether you want a telescope to look through or whether you want a telescope to do astrophotography. A lot of people choose a telescope that looks like this. It's called a Schmidt-Cassegrain. We're not going to worry too much about the technicalities. This happens to be quite a large telescope in which the light path is folded so that it gives you, in a sense, a very big telescope in a relatively small package. The front element here, the aperture, can be something of order 20 centimeters or 25 or 30 centimeters is fairly typical for amateurs. Some amateurs will take a telescope like that and immediately adulterate it by trying to add as many accessories as possible, because it looks like he who dies with the most cables wins. So there's cameras added on the back and extra widgets on the side and a little bit of a dew heater, because in the UK you can get condensation on very humid evenings, and so there are ways of trying to keep the front element warm so that you can do your astrophotography for many, many hours. But some people would say, some dedicated astrophotographers would say, if you are thinking of buying a telescope and wanting to use it for astrophotography, spend more time thinking about the mount on which the telescope sits rather than the telescope itself. Yes, you need, ideally, a telescope with good quality optics, but it is absolutely crucial, because the Earth is turning and hence the sky appears to rotate once every 23 hours and 56 minutes, which is the rotation period of the Earth. Because the sky appears to move, if you want to take reasonable length astrophotographs, you've got to make sure your telescope is capable of tracking the sky accurately. And some people would argue it is the quality of the mount that will dictate the quality of the astro images you end up with. I would sort of agree with that in principle. Of course, the quality of the telescope that gets bolted onto that does make a difference. But if you have a really good telescope on a really wobbly mount, you're never going to get some very good images. Whereas if you've got a good, steady mount, then any telescope you put onto that is hopefully going to work well. So that's good in principle, but then you can say, well, okay, in principle, yes, but is it worth $10,000 to buy yourself a really good, stable mount which can track the sky accurately? And by the way, if anybody is contemplating at all the idea of buying a telescope, either for yourself or a member of your family, don't jump in, don't waste your money until you've taken good advice, either from a local astro society, or I can point you towards a video of a talk I've given on a rough guide to how you go about choosing a telescope for yourself. If you did have a telescope, well, where do you put it? Well, you can either keep it indoors and take it outside whenever you need to use it, or you can have an observatory in your back garden. Okay, that's not a back garden, that's Mount Palomar in California. That was the home to the world's largest telescope when I was born. It was the world's largest telescope for most of my childhood, and it was the world's largest telescope for most of my adult life, and has only relatively recently been superseded by other telescopes being built around the world, such as Chile or Hawaii or Canary Islands. I visited it back in 1982. That's me. I think I'm actually wearing the same shirt as I did in 1982. And when I visited that, I thought, that's a wonderful dome. When I grow up, that was when I was a student, when I grow up, I'm going to have a house with a back garden big enough for a dome like that so I can put my telescope in. Okay, I had to downsize my aspirations slightly, and a few years later, I bought myself a B&Q shed and converted the roof into one that can be basically opened up to reveal the sky, and that's what the observatory looked like on the inside. You can tell it's a very old picture because A, it's clean, and spiders tend to take over observatories quite quickly. And you can also tell it's very old because the laptop looks like a brick rather than the very slim laptops that you get these days. But that's not a bad idea. If you are going to invest in a telescope, it's good to try and keep it in reasonable condition, and so an observatory in your back garden is no bad idea. And with a modest-sized telescope, you get superb views of the moon, and you can photograph the moon as well if you wish. But simply watching the moon, you shouldn't underestimate the joy you can get by looking at the features on the moon, the craters, the mountains, as the moon slowly rotates and the sun angle slowly changes. You see shadows cast on the lunar surface, and you can watch them from hour to hour throughout the evening. The amount of detail you can see on the surface of the moon through a modest-sized telescope can be absolutely stunning. And if you're lucky enough to be able to use one, this was taken with a 14-inch. I'm sorry, we have to use old-fashioned numbers because most telescopes are defined by the aperture in inches. We can always convert them into centimeters, but they're often defined in terms of inches. So this was taken with a 14-inch telescope, not by any means cheap. This one was owned by the university. So this was when we took our students to Tenerife and spent some time on top of the volcano there. And I took this snap. This is a snap of the moon taken in 1/500th of a second. The moon is a bright object with a big telescope. It's collecting a lot of light, so you don't need very long exposure to capture this. And you can see wonderful detail of the smooth mare, the beautiful craters, the smooth flooded crater here where basalt has basically flooded this crater and produced a nice flat floor. You get the wonderful mountain ranges. If we have a look at the bottom half of this image, I just blew it up so you could see it a little more clearly. The crater Copernicus, which is a prominent crater right in the middle of the moon there. So you can see wonderful detail by eye, and you can capture it just in a snapshot of click, 1/500th of a second, and you've managed to capture a beautiful image of the moon. With the same telescope, I also tried taking some longer exposures of other objects. There's the pillars of creation in the so-called Eagle Nebula. There's the pillars as indicated by the earlier picture taken by the Hubble Space Telescope, made popular by the Hubble Space Telescope. This was a somewhat longer exposure. You can't just take a 500th of a second. If you want to take faint nebulae in star clusters, you need usually many, many minutes of exposures. And again, I didn't take a very long exposure. I took a whole series of relatively short exposures to capture the pillars of creation there. And that same evening, I also took a picture of this. This is a so-called planetary nebula, nothing to do with planets. This is a star. That central dot right in the middle there is a star that many thousands of years ago basically blew off its outer layers. So this is a star coming to the end of its life, pretty much like our sun will come to the end of its life in another 5 billion years or so. This star has shed its outer layers, and those outer layers of the star have become this nebula. The nebula contains hydrogen and oxygen glows red and oxygen glows blue, and that's the core of the star that's left behind. This is the fate of our sun. In a sense, you're looking at a picture of what our sun will look like in about 5 billion years or so. One thing to note is that these colors are real. I'm not in any way trying to modify the colors of the images that I'm showing you. Hubble Space Telescope images usually are changed or modified or, if you like, false color in order to reveal as much detail as possible. So the pillars of creation that I showed you earlier from the Hubble Space Telescope were not real colors. This is the real color. Hydrogen glows red or reddish pink. Hydrogen is red, and here oxygen is blue. So we can tell what elements are present by looking at the colors in the astrophotos that you take. And a third picture, a rather beautiful nebula called the Trifid Nebula. Trifid because of the sort of three petals, if you like, of the structure at the bottom there, looking a little bit like a flower. And again, these are, as far as we can tell, as close to real as possible. There is definitely a whole load of hydrogen in the bottom part of this image, and there's a whole load of scattered light which is looking blue because blue stars are scattering a lot of light in the top part of the image. And it is wonderful to realize that this is the sort of thing that you can capture with a camera that's designed to work in daylight. My preferred DSLR camera these days is a Nikon. It happens to be a Nikon D7500, but it doesn't really matter whether it's a Nikon, a Canon, a Sony, or whatever. They are designed to work in daylight, and yet they still work amazingly well if you take pictures at night, and they give reasonably accurate color rendition. So that's not taken with the cheapest of telescopes, that's taken with a fairly large telescope under very dark skies, a sort of ideal situation. There's another type of telescope which is by no means the cheapest sort of telescope that you can ever get your hands on, and that's a telescope that's designed to work to take images of the sun. Never try and do this unless you absolutely know what you are doing. Taking pictures of the sun like this is taken with a very specific telescope, usually called a solar telescope, sometimes called an H-alpha or hydrogen alpha telescope, that only lets through one particular wavelength, not the whole wavelength spread of the visible light, but one particular wavelength, which then highlights all of the detail, not only the detail on the surface of the sun, sunspots and features, but all of these so-called prominences, these huge arcs of plasma, ionized hydrogen gas that erupt from the surface of the sun. And these change minute by minute, hour by hour, day by day. So again, if you're lucky enough to have a few days in which you get nice clear skies during the day, solar scopes can allow you to watch these features. And the sun is very active at the moment. This last few months, we've had a lot of very clear days during the day, and it's been possible to grab images like that. But do not try this with anything unless it's certified as safe to use looking at the sun. And make sure that message gets across to any youngsters that you know. So, before I take a break, I wanted to say, right, you can do astrophotography with very expensive equipment. Joking aside about buying the Hubble Space Telescope, etc., you can, if you wish, invest large amounts of money in astronomy and astrophotography. I work and have given talks to a lot of astronomical societies, and some individuals have got enough spare cash, either because they're retired and they've got a bit of cash floating around, or they haven't told the wife and they spend it on astronomy anyway. And some cases, they not only spend a fair bit of money on the camera, they can spend thousands upon thousands on the telescope and the mount, and possibly an observatory in the back garden. So yes, that is a very good way of doing astrophotography, but it has caveats that I'm going to come to. If you want to keep it modest in terms of the expense, and I would argue modest means almost zero if you do it right, you can take the camera that you already own and use what I call, or what are generally called, star trackers. So let me tell you about star trackers, and before I get stuck into the detail, we'll take a little break after I've introduced this topic. But I know you already know this, but it's part of the talk, so I'll go through it anyway. There's no such thing as a color camera. There are only monochrome cameras. So if you think of what happens in a monochrome sensitive device, whether that be a device which has photographic emulsion film in it, for those of you who remember that, or whether it's a CCD chip, the CCD chip basically responds to all colors. So light doesn't matter whether it's coming through a camera lens or a telescope, it's just light is focused onto the chip. If the film or the CCD is monochrome and we want to take color images, then we would need to put filters somewhere in the system. So we would either put them on the front of the lens, or between the lens and the film we would have red and then green and then blue, and we would take 3 images on the monochromatic sensor, whether that be film or CCD, and having obtained 3 color images, we would then combine them together to produce a color image. This is precisely what the Hubble Space Telescope does, except it doesn't necessarily use red, green, and blue, the 3 primary colors. It chooses filters that are of scientific interest. It chooses a filter that shows up where the hydrogen is. It chooses a filter that shows up where oxygen is. It chooses a filter that shows where sulfur is. So it doesn't choose red, green, and blue because that gives you an aesthetically pleasing result. It chooses 3 particular wavelengths of light to let through that tell you about the content, the composition of the object that you're looking at. Having obtained those 3 images, when you then combine them together, you can choose to take that one and make that the red channel of your final image, take that one and make it the blue, and that one to make it the green. It doesn't matter if those red, green, blue channels that ultimately give you a color image, it doesn't matter if they're directly related to the 3 filters you've used. That's just the convention that we're used to for producing color images. So how did that work when color film came along? Well, it was still monochromatic film, but very cleverly, they put the filters in the film. The film was basically multi-layer emulsions, such that the light was filtered as it went through the different layers and then produced a color image. And with CCDs, with charge-coupled devices or other electronic sensors in your modern digital cameras, whether they're digital SLRs or mirrorless cameras or the camera in your phone, that again is still a monochromatic CCD. The difference is the filters are now placed in front of every pixel in the entire array. No matter how many millions of pixels there are in your camera, basically red, green, blue filters are placed at the manufacturing level on top of the actual CCD. So it's still technically a mono CCD with filters printed on the top. So if you look at a color chip that's in your camera, then basically if we were to blow that up and say, what are we actually looking at? Well, there's a pattern of red, green, blue filters. It doesn't necessarily look like this, but it usually looks something like this. It's called a Bayer grid, in which the red, the green, and the blue filters occupy a particular pattern. And as long as the computer that's taking the images in the camera understands which one is red, which one is green, etc., it can take all the information from the chip and then produce a color image. In other words, what it's actually recording is what's happening in red light, what's happening in green light, what's happening in blue light, and then the computer inside the camera puts them all together and spits out a JPEG or whatever of your final image. Notice that there are twice as many greens as there are reds and blues. That matches human vision, because human vision is much more sensitive to the middle of the spectrum, green, than it is to red and blue. So it's very important that you get the green right for normal daylight images. You could argue it's actually less important for astronomical imaging, because most of the interesting stuff, like hydrogen, is actually the red end of the spectrum, and a lot of the other interesting stuff, like oxygen, is at the blue end of the spectrum. There aren't actually many things that glow green. There are red stars, there are blue stars, there are no green stars. And yet we have to live with cameras that are designed to work in daylight. So you could argue we shouldn't really expect cameras that work in daylight to be any good for astrophotography. And yet it turns out they're actually quite useful. Here's a random selection of just literally 3 cameras that I just picked off the internet. I'm not endorsing any of these. I'm simply making the point that you can get cameras that will replace an eyepiece. You can get yourself a telescope and look at the sky, and you can replace the eyepiece with a little electronic camera that's literally just that sort of size, the size of a 35mm film canister, for instance. And color cameras will start at a couple of £100 or so. If you are serious about astrophotography, some people will invest large amounts of money to get the best camera for whatever telescope that they use. And You could buy a mono camera or you can buy color camera. And perhaps it's a little bit surprising that the sort of costs that you might end up paying are actually the same. A lot of manufacturers will produce cameras in both varieties. A given camera with a given spec might be available as a mono camera or it might be available as a color camera. And the costs are often identical. There is virtually no additional cost to the manufacturer on making a CCD to then, as the final step, put the colored filters on the top. It virtually makes no difference. In other words, there's just a make the CCD option or make the CCD and before you've finished, put the filters down. Cost-wise, it makes no difference to them. Therefore, they're perfectly happy to sell you a mono camera or a color camera. And people will choose either, I want to take color images, or some people will say, no, I want a mono camera, and then I will choose which filters I want to put in front of the camera. That might be red, green, blue to give me nice images, or I might choose filters that let through hydrogen only, or oxygen only, or sulfur only, or calcium only. In other words, I want to actually, if you like, emulate the Hubble Space Telescope. I want to reveal particular content of these astronomical objects that I'm imaging, as opposed to, no, just give me a red, green, blue filter and I'll get some nice colored images. So it's entirely down to the choice of the individual which way they want to go. A so-called one-shot color where all the filters are built in, or a monochrome, in which case I will choose the filters. The cost, of course, is that you need to then buy something which then selects the particular filter. Usually it's part of the computer control. You basically say, I want to take an image of this particular object, and I want to use filter number 1 and then filter number 2 and then filter number 3. So take me, I don't know, half-hour exposures with filter 1 and then automatically rotate to the next position and take another half-hour of images with filter 2, etc. You don't necessarily have to babysit it. You can basically set it up with the laptop to actually dictate what the filter systems are going to be, and then you go away and hopefully come back to your 3 color images, 3 or more, given that you've got actually enough space to have 5 filters if you so wish, or more. You can pay more and you can have different combinations of filter. But I would argue that yes, you can spend hundreds or you can spend thousands of pounds on astronomical cameras, which you might then want to bolt onto your astronomical telescope sitting on your astronomical mount. You might already have reached something like £5,000 and decided that's a fantastic system. But the main thrust of this talk this evening is, haven't you already got a camera? I'm assuming, if I'm talking to a photographic club, most of you will already own a camera. It might not be a digital SLR, it might be a mirrorless, it might be a bridge camera, who knows what it is. But if you've already got a camera, why invest huge amounts of money when the camera you've already got is probably capable of producing some really nice images? All you need is to figure out a way of getting rid of the fact that the Earth rotates. This is the pain that all astronomers have to deal with. If the Earth rotates once in 23 hours and 56 minutes, then the sky appears to rotate once in 23 hours, 56 minutes. So at the very least, you're going to need to point your camera sitting on something which de-rotates the Earth, which compensates for the fact that the Earth is moving and hopefully keeps your camera fixed at a particular point in the sky so that you can take not necessarily hour-long exposures, but at least you can expose for many seconds or many minutes without worrying about the star blurring because it moves relative to the camera. So that's what I mean by a star tracker. A star tracker is the simplest way of moving the camera to follow the stars. This is one that I built. It's quite old one now. It's many years ago. But I decided to build myself a star tracker. A, because I didn't want to spend money, and B, I thought it would be a fun little project. So I decided to buy some, bits and pieces. It's a little bit of aluminium. It's a couple of door hinges. It's a couple of AA batteries. It's a little DC motor and a couple of switches. It'll cost you 10 or 20 quid, assuming you haven't already got the bits lying around in your garage anyway. If you wanted to go out and buy the bits, it would cost you something like 10 or 20 quid. And so I built that. The instructions are at the front here. I've printed out a few copies, and I will make PDFs available to you via Viv later in the day. So you can build one for yourself if you fancy it. If you don't fancy it, if you're no good with a soldering iron, not too sure which end is the hot end, then you can go out and buy yourself a star tracker. A star tracker, when I was young, there was no such thing. Telescopes were built on mounts, and there was no such thing as put a camera on a tracker. In the last 10 or 20 years, the number of trackers available has absolutely exploded. In other words, I think there are probably 10 different manufacturers of star trackers. They start at 100, 200, 300 pounds, depending on how sophisticated you want them to be. And after I used my own home-built star tracker for a while, I thought, let's give it a go. I decided to invest a couple of €100 in this particular tracker. I'm not saying that's the best tracker in the world. I don't think that one is available anymore, because I bought that about 10 years ago, and there are plenty of others. That particular one is made by a firm called Ioptron. As I say, I'm not saying that's the best tracker. It's just one of many that are available. If you Google star tracker, you'll simply find lots of them. It's basically a motor in a box that turns this disc at the top, and if you mount your camera on that disc at the top, then the camera will follow the stars, providing that you get the tracker lined up so that it rotates about an axis parallel with the Earth's axis. Remember, we're trying to effectively compensate for the rotation of the Earth. So we need to be on the same axis, and we need to move in the opposite direction at exactly the right speed. So what's in a star tracker? Well, essentially, it's very simple. What you're paying for is precision. It's a simple idea that batteries, via a little bit of electronics, run a motor and a gearbox, which runs a worm, which then turns this wheel. The idea is this wheel turns at exactly one revolution, not in a day, one revolution in 23 hours and 56 minutes, because that's the rotation period of the Earth. So hopefully it accurately derotates the Earth, providing you make sure it's lined up. So that's what it looks like. It's basically a white box. That little telescope there, little polar scope, simply allows you to make sure that you've got it lined up on Polaris, lined up on the North Star, to make sure that it's rotating about an axis parallel with the way the Earth is rotating. And as long as you point it in the right direction, then it should allow the camera to move. And you can see the camera is sometimes put on a little ball and socket joint. It doesn't really matter. So although this has to be lined up with the Earth's axis, the camera can point to any part of the sky you like. And so having a ball and socket joint is not a bad idea for allowing you to point at various parts of the sky, and you're not restricted other than you can't put a huge load on this. You can't put 10 kilograms of gear on something like this, because it would just fall over. But basically a camera and a wide-angle lens or a portrait lens or a telephoto lens, as long as it doesn't weigh more than a few kilos, and as long as you've got something like a ball and socket joint to point the camera in whatever direction you like, then a simple little tracker like this will allow you to do astrophotography. I've taken it as far as I can by taking my Nikon and a telephoto lens, and it still didn't fall over, and it still appears to track okay. I can't remember what the combination is, but that body and that lens weighs much more than a kilo, probably about 1.5 kilograms or something like that, and the tracker had no real problem moving a relatively large combination of DSLR body and telephoto lens. Before I take the break, which I'm about due for, let me just make the point that what I'm showing you are images taken by my Nikon D7500. I'm not taking a handout from Nikon. It just happens to be my camera of choice. And if occasionally I go on safari and take pictures of lions, my choice is a Nikon body with a 300mm f4 lens. And it just so happens that that camera and that lens work just as well with lions as they do with astrophotography. I chose that lens mainly because it was a reasonably long focal length. I thought 300mm was quite good, but it fits in the palm of your hand. I didn't want a telephoto lens which was longer than the reach of my arm, which would require somebody else to carry my lens for me when I went on safari. So it's a very small, very light, very compact lens. But it just so happens that that combination, which are designed to work in daylight and take pictures of lions, actually turns out to be a fantastic combination for astrophotography as well. There is no particular reason why they should work. Nikon and Canon and Sony and Panasonic make cameras to work in daylight, or at least good light, and yet they do actually work really well for astrophotography. So in the next section, I'm going to show you how those work and what sort of images you can expect to get by taking your camera and your lenses and putting them on a star tracker. So this is a good time to take a break. Thank you. Okay then, having had a tea break, let's pick up where we left off. I was telling you about how we can use trackers with the cameras that we already own rather than investing huge amounts of money in telescopes and expensive mounts. A tracker, in principle, you can build for yourself at very little cost, or you can buy commercially available trackers. So I'm going to show you a few of the things you can produce, a few of the images that you can get with. Okay, I'm talking about a digital SLR, but I don't think it makes an awful lot of difference which camera you're dealing with. The point is that if you put a camera on a tracker, you can take long exposures of many, many seconds without worrying about the sky moving because of the rotation of the Earth. And there's a little sample of some images I've taken with a tracker. So just to reiterate, I am not dissing the idea of buying a telescope. Yes, people have bought telescopes and put cameras on the back and produced stunningly good images. And you might have seen them in astronomy magazines or on web pages, etc. But the bottom line is, although it is very rewarding to do that, it will take time, it will take effort, and it will take cash if you want to do it right. And cash perhaps is the most important bit of that. It'll cost thousands of pounds, and you will have to invest a fair bit of time learning your craft, how to take the images, how to process them, etc. One point about processing: don't expect the image you get on the back of the camera, if you're using a digital camera, don't expect that to look perfect as soon as you've taken the picture. Here's an image taken straight off the camera. That's effectively what you would see on the back of the camera. This is a raw image. And it was taken from a suburb of a city which was rife with light pollution. And so it's very difficult to see the rather interesting nebula that is buried in the middle of that. However, with processing using either free software or software you can buy if you prefer, or something like Photoshop if you've already got that on your laptop or your computer, software can mitigate the worst effects of light pollution. So this is effectively the same image after being processed to get rid of this horrible orange glow in the background and make the sky a little bit darker, and to tease out the details that are in this particular pink nebula. Pink, so hydrogen. This nebula, which you might already guess is called the North America Nebula because of the outline of the California coast, the Gulf of Mexico, etc. So, with the caveat that you can't expect the back of your camera to show things instantly, generally speaking, you need to take the images from your camera and then do some processing to bring out these details. This is the sort of thing that you can do with a camera on a tracker. I've kept the information down the bottom. So this is a Nikon with a 300mm lens. And remember, I don't tend to take long exposures of an hour or so. I take dozens, if not hundreds of images, each of which is maybe 30 seconds. That means if there's passing cloud, I can throw those away. If there's a passing satellite, I can throw those away. If there's a passing aircraft, I can throw those away, pick out the good ones, add them all together using software to get the final image. Notice that the stars are showing relatively nice colors, red stars, blue stars. There are no green stars. And the actual nebula itself, this is a nursery of stars being born. So these stars right in the middle, that star cluster, is a star nursery. So this is where stars are being born. It's the so-called Rosette Nebula in the constellation of Monoceros, the unicorn. This is the opposite end of the life and death story, because this is a star coming to the end of its life rather than stars being born. This right in the heart here, too bright to see in this particular exposure, this star is getting very unstable. It's a very massive star, and we think this star is coming to the end of its life. For thousands of years, this star has been shrugging off some of its outer layers, and the nebula you can see here, the pinkish region all around, is part of the outer atmosphere of the star, which has now been shrugged off, and the star itself is still in the middle there, still going, still fusing energy to produce light and heat, but we think it's due to go supernova in not too distant future. That could be tomorrow, could be in 1,000 years, we don't know. It's almost impossible to predict. All we know is this is definitely coming towards the end of its life. It's in a part of the sky called Carinae. It's called the Carina Nebula. This is a star that's already gone bang. This is the result of a supernova. We don't know which particular star it was. It's probably not visible at all. This is a bubble that's been produced by this star exploding 15,000 years ago or thereabouts. So this star went supernova a long time ago, before recorded history, so there's no record of it anywhere. But we think this is about 15,000 years old, and it's effectively a large bubble of gas, again the same colors. Pink indicates hydrogen, blue indicates oxygen. So this particular star seems to have produced a lot of oxygen as well as quite a bit of hydrogen. This is the only image I'm showing you in which I've used a filter. And this particular filter is a filter that's quite useful for getting rid of streetlights. It's a filter that lets through the light of hydrogen and the light of oxygen, but it effectively kills the light of LED streetlights. This picture was taken from outside my front door, about 10 meters away from a streetlight, and yet the filter managed to effectively cut out the light pollution and allow us to pick out some of the faint nebulosity that you can see in this large shell of gas. So I did this as an exercise, as an experiment, if you like. All the other images I'm showing you, no filters at all, other than those that are in the camera, of course. This is a very colourful nebula in the constellation of Scorpius and the neighbouring constellation of Ophiuchus. There's a very bright star here which is lighting up this part of the nebula, producing this yellowy orangey colour. There's a blue star over here which is lighting up this part of the nebula blue. There's a little bit of pink down the bottom, indicating we've got some hydrogen in there. There's also a star cluster there, this sort of rather large blob at the bottom. I can sort of label these. Antares is a large red giant star. That's a star cluster. That's a blue star called Rho Ophiuchi. And the whole area is covered by the beautiful colors, and notice these dark nebula, these regions that block out the light from more distant stars. And when I originally took this, it was a 135 millimeter lens. Remember, you don't need the longest focal lengths necessarily. It's something I forgot to mention on the previous image, but the one of this Eta Carina, I forgot to mention that this is actually an 85 millimeter lens. These objects are, yes, quite distant, but not necessarily that small in the sky. It's not like you need a 1,000 millimeter telephoto lens in order to pick out these objects. 85 millimeter, it's basically a portrait lens. These things are huge. Some of them are huge in the sky. And the same is true of this. It's a relatively large nebulae, so I used a 135 millimeter lens. But I did return to it some years later thinking, I wonder what it would look like if I used a 300 millimeter lens, in which case I'd obviously have a much smaller field of view. So I returned to it some years later and took a 300 millimeter of the same area with the yellow in the top left and blue in the bottom right. And you end up with something that looks like a watercolor. The amount of information you've got in there is stunning. So yes, it's a relatively long exposure, 150 exposures, each of which is 1 minute. 1 minute tells you that yes, you can quite happily put a long focal length on a star tracker, and as long as you've lined it up to the Earth's axis, you can take pictures for 1 minute quite happily, and the stars still end up as pinpoint. The stars don't move as long as you set it up correctly. But to get these beautiful colors coming out, and remember these colors are natural, no filters, no artificial coloring. This is the genuine colors of this particular nebula complex, yellowish, bluish, and these dark regions as well. It produces some stunning images when you take long enough exposures. And generally speaking, the trick here is to take as much data as possible. Don't assume that you can take 1 minute's worth of images and that's all you need. You ideally want many, many, many images, the more the merrier, such that you get all of the detail coming out in these faint nebula. And you're not restricted to looking at what's going on in our galaxy. There's our neighboring galaxy, the Andromeda galaxy. Again, 300mm lens. So the Andromeda galaxy, for instance, is much bigger than the full moon in our sky in terms of angular size. Yes, of course, it's a galaxy, so it's a lot bigger, but it's a lot further away. But in terms of how big does it look in the sky, it is about 3 degrees across, which is much bigger than the half a degree of the full moon. So it's actually a very big galaxy, and a 300mm lens captures it very nicely. And again, you can see beautiful detail in the spiral arms of this galaxy, which is seen not face on, not edge on, but at a jaunty angle. And these smudges here are a couple of satellite galaxies. That's by no means the most distant object we can capture with a camera on a tracker. I thought, is it possible to capture a galaxy group? So I tried something else. This is a whole string of galaxies, a chain of galaxies called Markarian's chain. They appear to be gravitationally bound to each other. They're not just scattered randomly in the sky. These galaxies were presumably made at the same time and seem to be gravitationally tugging on each other. A whole series of them in that chain and a few others in the group. In this particular image, I looked very carefully and checked it against the star atlas. There's probably 50, 60, 70 galaxies in that one image alone. All of these galaxies are at the distance of about 50 million light years. So in other words, the light left these galaxies 50 million years ago. When the light left these galaxies, well, dinosaurs had only just died out, basically. And when you start looking deep into the universe, you have to get used to the idea the light left an awfully long time ago. When you're taking pictures of something in daylight, you take a picture of a dog or you take a picture of a flower, you don't think about the light traveling from the object to your camera because it takes just a fraction of a second. If you take a picture of the moon, you're taking a picture of it as it was 1 second ago, because that's how long it took the light to come from the moon to the Earth, because of the finite speed of light. 300,000 kilometers per second sounds really fast until you're talking about these vast distances. And here we've got 50 million light years. But I wondered, okay, I've got a camera that's designed to work in daylight. What is the most distant thing I can capture with this setup of a camera and a telephoto lens on a star tracker? I thought about that idly until along came 2020. Couldn't go to the pub because of COVID lockdown, so I thought, okay, can't go to the pub, what do I do this evening? Oh, let's try something, let's try an experiment. Let's put the camera on the tracker and let's see if I can catch the most distant object. So I looked up in a paper a very distant galaxy called a quasar. A quasar is a galaxy with a very bright nucleus, which hopefully I can capture from a great distance. So I got my tracker out, put the Nikon with a telephoto lens on the tracker, and pointed it where I thought this quasar ought to be, according to the information I had gleaned by somebody else's survey. That's not it in the middle, that's just a star that happens to be quite close, and I used that to basically point my camera in the right direction. I also used that star to focus on to make sure that everything was okay. And then I took as many exposures as the July night would allow. And in the middle of summer, of course, we don't have much night. Basically, from evening twilight to morning twilight, there's about 2 hours of darkness. So I basically set up the camera with an intervalometer and told it to take 30-second images and just keep going. In the end, it took about 256 images, each of which was 30 seconds. So in other words, it ran for about 2 hours. It actually ran a little over 2 hours, but I threw some of those frames away because cloud came over whilst I was indoors, and then the clouds cleared. So I ended up with about 2 hours worth of exposure in total. I hope the quasar is right next door to that star. After I had stacked all these images together to make my 2-hour exposure, I then looked in the middle of that square because that's where I expect the quasar to be. This is almost certainly the least impressive photograph you've ever seen in this club, because that is the quasar. I am absolutely sure that's the quasar because I can check the pattern of stars, and there are bits of software that will allow you to confirm the coordinates of any dot in any image. That is the quasar that I was trying to photograph. Most of the light from this particular quasar, most of the light from this galaxy is actually focused into 1 pixel. And if I blow it up, there it is. Again, the least impressive picture you'll ever see. I don't care about most of the 19.9999 megapixels in this image. I just care about the fact that for 1 and maybe the surrounding pixels, it's caught the light from this galaxy. What is stunning is not the fact that there's a blob in the middle of that square. What is stunning is how long that light has taken to reach us. This object is 25 billion light years away. The light has been traveling to reach us for 12.4 billion years. The universe is only 13.8 billion years old, and the light has been traveling for 90% of that. In other words, the light left this galaxy 12 billion years ago, and for 8 billion years, the light was traveling before the Earth even existed. Then the sun was made, and the Earth was made, and the light traveled on. Life arose on Earth, and the light traveled on. Dinosaurs came and went, and the light traveled on. In the last 1,000,000 years or so, the light came into our galaxy, crossed the spiral arm, entered our solar system, headed towards Earth, dodged a few clouds, and eventually hit the camera sensor on a clear night on the Wirral. So the journey was 12.4 billion years, most of the age of the universe. And a camera designed to take pictures in daylight was able to capture that light. The universe is expanding. I'm not sure that comes as a surprise to you, but we've known for 100 years or more that the universe is expanding, so very distant objects are actually receding away from us. This object is so far away from us, it's actually receding from us at twice the speed of light. So the light that left this galaxy was actually being dragged backwards because of the expansion of the universe, and it took billions of years before the light finally made some headway towards what eventually would be planet Earth. So the story of the photons of light that produced that little white cross there, the least impressive looking image, but the most incredible journey that light has taken in order to produce an image. The Hubble Space Telescope is capable of looking at objects more distant than this, but not by much, only by a little more. I've gone back 12.4 billion years into history to take that image. The Hubble Space Telescope can go back about 13. So a Nikon can go 12.4, the Hubble Space Telescope can go to 13. Nikons aren't cheap, but they're a damn sight cheaper than the Hubble Space Telescope, which cost about $10 billion or so. So the fact that you can do this with the camera you've already got, I just find absolutely stunning. So let me just finish with a few points about going on safari. Friends and I are interested in wildlife and wildlife photography and in astronomy. So if you're going to Africa, well, you might be interested in wildlife, in which case you take a pair of binoculars to look at the wildlife in the distance. And if you're going into the middle of nowhere, into the bush, you're going somewhere incredibly dark because you're getting away from light pollution. There are no street lights out there. So you can also use those same binoculars to do astronomy at night time. And of course, if you have an interest in photography, which you all do, then you are interested in wildlife photography, the overlap of the green and the blue, and you might also be interested in astrophotography, the overlap of the red and the blue there. So basically, if you go on safari, you get all three hits. You get the wildlife, and you get the astronomy, and you get the options to do photography. Basically, on the left, on safari, you can do animals by day, stars by night, sleep when you get home. There's no point in wasting time when you're out there. Okay, I haven't quite got the stamina I used to have, so sometimes I stay up for a while to do astrophotography, but eventually you have to hit the sack ready for the next day on safari. When you're actually using a tracker like this, again, each tracker will be slightly different, but when I set up this tracker, I make sure this is lined up with the Earth's axis, and a little app basically tells me, well, I know where we are from GPS, and I know exactly what the time is, and therefore, if you want to set this exactly on the North Pole, directly above the Earth, then you should look through this little telescope, and Polaris should be at that position there. So literally, you just plonk it down on your tripod, and you adjust left, right, up, down, etc., until Polaris is where the app says Polaris ought to be. If you've got Polaris in the right place, then your scope, and hence your tracker, is lined up exactly on the North Pole, exactly to within a minute of arc or so, within a fraction, a very small fraction of a degree, more than enough to deal with pictures taken with wide-angle lenses or telephoto lenses. And once you've lined it up, well, that's a bit of a catch, because that's easy to do in the UK, because you can see Polaris. But bear in mind that the North Pole of the Earth, there's the North Celestial Pole, the point directly above the North Pole of the Earth. So from the UK, you can see Polaris. It's sitting there quite high in the sky. You can set up your tracker on it. But if you go to East Africa, like Kenya, well, Kenya's on the equator. So where are the North Pole and the South Pole? They're on your horizons. And so you can't see Polaris because it's hidden behind elephants or hills or something else. And you can't see the South Pole either for the same reason. Both poles are on both horizons. So unfortunately, to set up a tracker on the equator, you can't simply point it at Polaris or point it to get Polaris where it should be. You have to resort to old-fashioned means and say, well, I've got a compass here, and I think north is, I think north's that way, and you just guess. And hopefully, guessing is good enough. And it does allow you to take pictures of, for instance, the Milky Way. This is not quite what you see from Africa. That's my attempt to indicate what you might see from the UK if you go out and get away from streetlights. But when you go to Africa, the amount of detail you can see in the Milky Way is absolutely stunning. Simply with the naked eye, you can see the bright patches and the dark, dusty areas of the Milky Way. Sometimes it seems like the Milky Way casts shadows when you get really away from light pollution. And of course, as soon as you start taking images, then you get color. Your eyes don't react to color because the light levels are too low, but as soon as you take images, you can bring out the colors that are there. So the center of our Milky Way galaxy is actually that point there. It's a little bit too far down as seen from the UK, but if you go to latitudes such as the equator, then the center of the galaxy is high in the sky and relatively easy to image. And if I finish with just a little bit of navigating around this central region, the bright star there is not a star, that's actually Jupiter, which happened to be in the shot at the time, and over on the left, that is Saturn. And with images like this, you can't see perhaps on this screen, but if you've got it on your computer monitor at home, you can zoom in and you can see all sorts of star clusters and nebulae and other interesting things, which have already been catalogued by Europeans such as Charles Messier, who produced his catalogue of so-called M numbers or Messier numbers, and I've just labelled them. That doesn't mean anything to you, but there's lots of these Messier numbers, interesting star clusters and nebulae and other objects. You might say, well, that's weird. Why aren't there any interesting M numbers down the bottom right? It seems to be barren down there. Well, no, there's loads of interesting things down there, but Charles Messier was a Frenchman, and from France, you can only see so far down on your southern horizon. When you go to the equator, you can see much further south. So that was the limit to what Charles Messier could see back in the 18th century. So my message to you is, yes, if you wish, by all means, spend thousands of pounds on telescopes and produce wonderful images if you're prepared to put in the time and the effort and the cash. But one alternative is build yourself a star tracker or buy a reasonably modest little star tracker like this white box here. Use the camera you've already got. Use your wide-angle lenses, use your portrait lenses, use your telephoto lenses. If you're going on safari, if you're going somewhere abroad, doesn't have to be on safari, if you're going somewhere where you are going to be getting away from street lights, adding a little tracker which weighs, 800 grams, maybe a kilogram or something, put that in your luggage as well as your camera and your tripod, and then if you can get away from street lights, you'll be able to take images like these. Thank you for listening.